Hello and welcome to Dan Makes Things. My name's Dan, and over the last few years I've been building a companion robot and an open source robotics framework. As part of the release of the Raspberry Pi 5, I want to use the opportunity to upgrade the printed circuit board that's included in the head. The original PCB was built in Fritzing and had a very simple layout using available modules. As the project has grown, I've added additional modules and features, and they don't fit on this version of the PCB. And I want to use a piece of software that can make custom parts to make the process a lot easier. I decided to use KiCad in order to do this, as it was recommended to me. I'm going to take you through the process of creating your own symbols, footprints, schematics and PCBs, explain the function of each element and how everything ties together to create the PCB. First of all, let's take a look at a schematic. This is the schematic for the new PCB. The schematic editor gives you a logical view of how everything is connected together, regardless of the real-world layout of the components themselves. This represents the microwave sensor that's used to detect human presence. Let's take a look at editing a symbol. If I go to the symbol editor, you can see you have a list of libraries. Each library contains a number of symbols that you can view and edit yourself. Each of these lines represents a pin on the component that you can connect via wires to other components in your PCB. You can also create your own libraries. I've created the MakerForge Components library, and within that I've added a number of components. You can see here that same microwave sensor component. I've specified the voltage and ground pins as well as the output to the GPIO and the other two pins that are currently not used in my design. There are a number of tutorials that talk you through this whole process, and I'll link to some of those videos in the description as well. Alongside the symbol representation, you would also need to define a footprint, which is the representation of it in the physical world. You can jump into the footprint editor, and then within that you can see I also have the custom library. Then I can load up that same component and you'll see it looks totally different to how you'd expect it to based on this. Each of these pins have their own number, and what we do then is we add pins to the board that are auto-numbered based on the numbering sequence that's provided in the symbol. So physically speaking, each of these will be a through hole that you can connect your header pins to in order to connect this to the PCB. The purple box represents the outline, the dimensions of the board for this particular module. In this case, I actually also have a smaller version of this, which I'm using because I don't want the entire PCB to fit on top of mine. I actually wanted to overhang a little bit just to save some space. So what that looks like in the main schematic is if I jump into this page, I can actually specify which footprint I'd like to use, whether it's the full height, full sized part, or the minimal one as I've chosen today. The rather time consuming task is going through and linking up all of the components to all of the pins on the GPIO within the Raspberry Pi, but once that's done, the entire process becomes a lot more simple. You can see on the board I have the Raspberry Pi here, and then I have an audio amplifier to connect to a speaker, and I have two MEMS microphones, and these are both connected via the I2S interface on the Raspberry Pi. On the other side you can see I have an I2C to NeoPixel driver that takes an I2C signal and then outputs to a number of NeoPixels. 4 mini NeoPixels which are going to be surface mounted on the board, and then a JST connector which is going to connect to the LEDs in the eye. I also have things like a expandable I2C module connection via a JST pin, a 5-volt module, a 3-volt module, power connector, the serial connector, and then room to add a servo. And you'll notice this logic level converter as well, which converts the 3 volts from the Raspberry Pi to the 5 volts used in these other devices. One last thing to mention is that although there are a lot of wires on here, I've simplified it slightly by adding power symbols for the 3 volts, 5 volts and ground, and that allows us to link them directly rather than having wires running all over the place to the individual power symbols. So once you have your schematic defined, you can jump over to the PCB editor and start adding your footprints in order to create the routing, which we'll talk about. So as I go over to the PCB editor, you can see I've already done quite a bit of the layout. So the Raspberry Pi is represented here by a 40-pin header, and the other components drop in with their footprints that I've chosen. So you can see all of these are JST connectors. This is a connector for a servo. These are surface mount NeoPixel slots. And then I also have some headers for the I2C to NeoPixel driver. The buzzer is going to go in place there. The amplifier is quite large, is going to fit in there. And then I actually have two microphones, and what you can see is that one is on the front of the board and one is on the back. That different color represents the back of the board. You can confirm that by hiding certain layers on the PCB to see what applies to each layer. You can see here as well that microwave sensor that would normally extend over the top of the board, and for the sake of simplicity I've made that smaller because I like that to extend out the top. Finally, the logic level converter is there. Normally, simple PCBs have two layers. You have the front and the back, and you can add wires or traces from the components to other components, either running along the front or the back of the board. For more complex PCBs, you actually have the ability to add multiple layers above and beyond those two that are on the front and the back. And in KiCad, you can do this by going into board setup and specifying in the physical stackup the number of copper layers. My board is a 4 copper layer board. You can see the layers defined down the right hand side here. We have the front copper layer, the inner 1, inner 2, and then the back copper layer as well. Currently there isn't really anything routed on any of these, but what I want to do is show you how you can use power planes to make your routing a lot more simple. At the moment we have grounds defined on most of these. We have either 5 or 3 volts defined on the others, and if we were to route all of those with individual traces, the whole thing would get very complex, even with the 4 layers in play. So what's generally recommended is that you create power planes. Now, power planes are effectively entire layers that are solely for the purpose of routing power at whatever voltage you define. In order to do that, you select the layer, then you select Add a filled zone, and then click the first place you want that filled zone to appear. Then you have the option to specify which voltage you'd like it to work with. So in this case, I'm going to add a 5 volt, and I'm going to click OK. Then it gives me the option to draw the layer across the board, and I'm just going to roughly do that. We can edit that later. And once it's complete, you have a completed plane. Then what I'll do is right click, and I'm going to say Zones, Fill All Zones. And what that should do is work out which of these header pins should be connected to this 5 volt layer. So you can see immediately that some of these actually have almost little crosses across where this painted copper element is going to interact with the through-hole components. If I zoom in, you can see that each one of these is defined as 5 volts. And because we've allocated those header pins to 5 volts, the PCB will know that it needs to connect all of those via these. You can see that the ground pins aren't connected yet. And as we go along, we should find that the 5 volt is connected there as well, as are any other 5 volt elements that are defined. 5 volts there and 5 volts there. Now we can do the same thing for the ground plane as well by selecting the ground plane layer that I've just arbitrarily decided is inner 2, and then doing exactly the same thing again, and this time selecting ground and clicking OK. I can go through and highlight this, and then to make it more simple, I'm going to hide that other layer. I'm going to escape out of that. I'm going to right click, select, and I'm going to right click and say Zones, Fill All Zones, and now it should understand that that is the ground plane. And when we zoom in, you can see the 5 volt is not connected to this layer, but all of the ground pins are. Ground on power is connected, ground on the servo is connected, and so on. Now the exception to that is these. These are the surface mount components for the NeoPixels. They're not connected to the ground plane, and that's because there isn't a way of connecting surface mounts, something that's on the front of the PCB, to something that's on the inside of the PCB on a different layer. So what we need to do is we need to do that ourselves through vias. You can see this option to add a freestanding via, and I can select that, and then with the layer selected I can click on the board and it will add a ground via from the surface layer all the way down to this currently selected ground layer. Then if I press X, beg your pardon, then if I go back to my front layer, hover over the ground surface mount, press X, and then move it over to that via, you can see that it connects and that it understands that that's a ground link. Sometimes you might want these to be thicker, so generally what you can do is specify the width. You can either do that by selecting them both and changing the track width, or if I undo that, you can actually create your own custom track widths, and I'm going to make that about 0.5 mm and just go through the same thing again and select it like that. And that will mean that there's a little bit more current can go through that without causing any problems. So I'm going to go ahead and do exactly the same thing for all of the other ones. So selecting that same layer again, and then I can change my grid size to make it a little bit smaller. That's going to make it closer to that component. And we'll just do that for all of the grounds that aren't currently routed to ground. And we will also grab this guy and move him a little bit closer as well. And then I need to go back to the top layer, make sure I have my track width selected, and then connect all of those up. Very simple, very straightforward process. We need to do the same thing for the 5 volts, but obviously in this case that needs to be connected to the other layer, which is the green one. So to make things simpler, I'm going to hide the copper for the ground and include the power plane for the 5 volts. I'm going to get my vias and I'm going to put them as close as I can to that 5 volt rail there. And then back to the front, and again pressing X now, we're connecting those to that 5 volt, and it confirms along the trace that it's 5 volt. So that's those connected in terms of power. The next step is going to be to route them up correctly to the input and output. So let's jump back into the schematic and you can see what I mean. Each of these quite clearly has a link from the I2C driver to the digital input, and then from the output of the previous LED to the digital input. They have to be connected in series so that they can be addressed individually. And even once the signal goes through this JST connector to the I, those are connected in series as well. So we need to make sure that this first one is connected and routed correctly from the I2C driver and then all the way through to the JST. So we can see here, we know that these are the I2C pins, and this one is the output for the neopixels. So what I need to do again is go through and route that. Now I don't need it to be as thick because this is just a data signal. So I'm just going to pick the smallest option available, and I'm going to go around here and I'm going to try and get it into the end. Now you can click as many times as you need to. The key here is to not have any corners, any 90-degree corners, and obviously not be interacting with any other parts. Now we're fortunate because the ground plane is already connected, so we only really need to worry about interacting with these or any of the vias that we've placed. Now that that first one's connected, it's quite trivial to then go through and connect the others, and you can connect that and then do the same for the others. And then finally at the end here we have a connection between pin 1 to pin 2, and we can confirm if we're not sure because we can see that the output is pin 1 on the schematic and pin 2 on the JST. And that's it connected. So that is all of the neopixels connected, the 5 volt and the ground connected. So in theory, if we wire up the rest of the I2C driver, they should work just like that when I print the PCB. The process for routing the rest is exactly the same. You specify which layer you want to add the route to, and because we've taken the two middle layers for 5 volts and ground, it means we're limited again to the front and back layer to route the rest of these. So for example, if I did want to add the serial connections on the back layer, I just select the back layer, I would hover over and connect these two, and it's as simple as that. And you can see that they're represented as a different color, and if I hide that, you can see that they disappear and that the red ones disappear if I hide the other layer there as well. Now, it's generally recommended that you use manual routing in order to make sure that it is the best design possible. However, if you're looking to just get a feel for how things work, or if you're comfortable with auto routing, there is auto routing available in KiCad as a plugin. In order to use that after it's been installed, you go to external plugins and select free routing. If you wait a second, it should show up and it's going to give you a warning that it's going to attempt to route. I'm going to cancel that, because one thing that I do want to do is go into the settings, go to auto router, and I'm just going to disable those two copper layers. The reason for that is that if I didn't do that, it would go in and try and use those and actually add additional traces to those layers, which I don't really want to do. I want to try and keep it on both the front and back layers. Once I've done that, I can click Start Auto Router, and we should see it attempting to route all of the other traces by itself. You can see it's tried several different versions and then managed to find something that it believes is appropriate. So let's go in and have a look at that. Now, there was a reason why I decided to route these myself first, and that was because I knew the connection that I needed to make, and that the other ones I'm quite flexible on. But it means now we can go through and we can make changes here if we want to. What you do need to be careful of is that it has actually routed it as you would expect it to, and that nothing is overlapping, and there's no chance of any connections causing problems, and that the thickness of these routes are appropriate for the kind of work that's being done by the wire. You can see all of the 3 volts are connected there as well, and they chain them typically together, so you need to be mindful of that. Do we need to have a little bit of a thicker trace because there's going to be a lot of power drawn by these elements? In this case, I don't think it's too much of a problem, but I'll probably increase the thickness anyway, just to be safe. Once you're happy with your PCB, you can go through and make it ready for print. And the way you can do that is go to Fabrication Options and select the first option there. This will generate the files that you need. As part of this process, you need to make sure that your PCB follows all of the design rules. Click Run DRC in the bottom left, and then again Run DRC here. You can see here that some of the design rules that I've specified are coming up as errors. So in this one, we can see that in a certain connection that goes through to pad 6 of the J1, which is actually the Raspberry Pi, we have a minimum spoke count of 2, but actually only 1 is being connected. Now, what that means in practice is that if I zoom in there, you can see there is 1 trace connecting between the ground pin and the copper, but the rules of this PCB suggest that there should be 2, and so that's something that I need to resolve. If I go to the board setup and go to constraints, I can see the minimum thermal relief spoke count of 2. I can just change that down to 1 if I want to cheat, and then I can go through and try and do that again. And you can see now there are no errors, and therefore I should be able to generate this output. Then you should be able to see those files are being created, and what I can do is go through and select them all, create an archive or zip, and then I can navigate to a PCB manufacturer, and in this case I'm going to use JLC because they have been very good with previous PCBs and I'm quite happy with their service. I can select the zip file to upload, and their service will automatically process the file, understand the number of layers and dimensions, and give me a price. You can see it's already processed those elements, and the price calculated is $7. You can then go through and customize things such as the color. Another feature you might find useful is you can convert this to a 3D model in order to see how that looks. So you go to View, 3D Viewer, and let it do its thing. And what you then see is a new window open up that actually has a full representation of your PCB in 3D with the appropriate headers and other spaces added in there as well. Now I can see immediately that I've made a mistake here by adding one of the components to the back of the board and one to the front, so I can make a change there as well. And in this case, what I'd like to do is add both of them to the back of the board because I'd like the power to come in from that side. So I can close this down, go back to the power, and then just say change side or flip, and that will move that back to there. Then one thing that I have done, of course, is I need to reroute copper in order to make sure that that is now connecting the right way around as well. Which is zones, fill all zones. And what we should see is the ground is now connected, and then if I hide that and show the 5 volt, the 5 volt is now connected as well. Once again, I can save that, and I can say View as 3D, and we should see now the front of the board doesn't have either of those elements, and then as I rotate, you should see the power and the serial on the back as well. I hope you found this video useful. The links in the description will give you more information on how to use KiCad, as well as playlists from people who actually know how to use it. I'm not an expert, I'm learning as I go, so please make sure that you check your work before you create PCBs based solely on my advice. If you liked the video and you'd like to follow for more updates, please subscribe and take a look at the playlist in the description below. Thanks for watching.